You go from state P to R, and then with this you go from R to state S, and then from state S you go to Q. So effectively you've gone from P to Q. So, and you assume that the derivation from this to your string Y, that occurs in less than k plus 1 steps. In fact, it would be k steps, so a bit of a question mark why it's k. Why isn't it k minus 1? Okay. Well, anyway, so this is the number of steps needed to go from here to here is less than k plus 1. That's the essential thing. All right. Okay, so when you read your string Y, so that takes you to state S. Okay, leaves T on the stack. Then you read your B. It goes to state Q from here using that rule. So now when you popped that T here, you're left with an empty stack. Okay. And it's left in state Q. All right. So that works. Okay. You've proved it. You've proved it for this case. APQ goes to little a, big A, RS, little b. Right. Now let's do the other case where that's the case when your stack empties between the times when the PDA is in state P and Q. So it's empty some time in the middle of those two moments. Okay. So now let this it would generate Y, the substring Y, and this one let it generate substrings Z, Y, Z. Okay, so that generates substring Y, and this generates substring Z. Substrings of your X, they're portions of your X. Now, so I don't know if you can see it here. So in the case when you've got a second or more clearing of your stack, the appropriate variable, your APQ, that would then be overwritten, substituted. It'll go big APR, big ARQ. Right? And now this one, that generates your X, Y, the Y substring of X, and this generates the Z substring of X. And so you'll have like YZ here. So your X will just be YZ, right? Here. Right. Now what? Now this, your PR here, the number of derivations it needs to generate its substring Y, well, that'll be, now that makes sense, at most k steps. Maybe this should be at most k steps. Maybe that would be okay, at most k steps. Anyway, so the number of derivations to generate its string will be less than k plus 1. Right? That's our point. And similar logic for this one. Okay, because we're assuming that big A PQ that takes k plus 1 steps. That was the assumption. Right, so these two parts, if you like, a little big APR and big ARQ, both of them will take less than k plus 1 steps for the derivation, respectively. Okay. All right, so we can use the induction hypothesis. so this little y here, substring, that if you input that into your PDA, your P, that will successfully take it from state little p to state R. Okay, and the other one, the ARQ, that will successfully take the PDA, your P, from state R to state Q. Where is that? So the first one, APR, will take you successfully in generating the string Y from state R to Q. Okay, and the second one here, you assume that it successfully will it generates the string Z, and that Z will take the PDA from state P to Q. Okay. Well, that means the two together. If the two together, this will take you from state P to R and clears the stack, and then this one takes you from state R to state Q, clearing the stack. So the result of doing this and this will be you're going from state P to state Q with the stacks cleared at the beginning and the end. So that also works, right? So that's the proof completed for the second case, and hence that's the complete proof now of claim 2.30. Okay, now we go the other way. Now it's like a part of a part of a part. Quite a long proof. Okay, so now we go the other way. So you've got the string X. So if that string can take your machine, your PDA, from state little p with an empty stack to state little q with an empty stack, then this variable here will generate that string X. This is what this is saying. Right? So we're going the other way. This is the second part of an if and only if, that the two are equivalent. Okay? So effectively is saying that big A PQ will generate the strings X, will generate the strings X, in the style of a grammar, and that string X, or substring X, that will cause the equivalent PDA to go from state little p to state little q, and then we're trying to show it both ways. So and now we're saying what? Now we're starting with the PDA. So if this substring X takes the PDA from state little p, with empty stack, to state little q with empty stack, then this variable will generate that. The variable will generate the same string. Right? Before we did the other way, we started there. If this happens, if this variable here generates that string, then the X, the same string or substring, will take the PDA from this state to that state. But now we're starting with it. So the PDA, that's a given. It starts in state little p with empty stack and goes to state little q with empty stack. Right? So now again we have to prove that by induction. And this time, now induction always involves an integer of some sort. So what's the appropriate integer in this context? It will be the number of steps in the computation of the PDA before it was the number of derivations. You know, that's in the grammar context. This time we're in the PDA context, and a step would be you know, a state transition, you know, a move, if you like. Oh, a step in the PDA is like reading one symbol and making a state change. Okay, so how many steps in that sense does the machine, the PDA, go through to read the string X that's input, the input string X? Okay, so we're assuming this to be true when there's I'm going to start with 0. It's usually a small number. So the basis step in the induction, we're going to start, the computation has 0 steps rather than 1. I need to change the camera.